Welcome back to the deep dive. Today, we are diving into solar geoengineering.
Yeah, and this one is, it's a pretty wild concept, I gotta say.
It really is. So, to start this off, I want you, the listener, to picture something with us. Just think back to the summer of 1991.
Right, over in the Philippines.
Exactly. There was this mountain, Mount Pinatubo, and it just completely blew its top. It was this incredibly violent volcanic eruption.
One of the biggest of the 20th century, actually.
Right, but here's the crazy part. The most shocking thing wasn't really the explosion itself, as huge as it was. It was what happened right after.
Right, the aftermath.
Yeah. For the entire year following that eruption, the whole planet cooled down.
By about a full degree Fahrenheit, yeah.
A whole degree. Just from one mountain exploding. And so, that brings us to our mission for today. We've got this massive stack of scientific reports, historical climate data, policy studies,
Lots and lots of reading.
so much reading, and we are exploring this really, frankly, terrifying question that some scientists and even billionaires are starting to ask out loud.
Which is, what if we did that on purpose?
Exactly. What if we built a massive fleet of custom airplanes to mimic that volcano and manually dimmed the sun?
I mean, when you just say it out loud like that, it sounds completely absurd. Like the plot of a sci-fi movie.
It really does. Like some cartoon villain scheme.
But the mechanics behind it, the actual science, is deeply rooted in atmospheric physics.
Right.
It's totally based on those natural events, like the volcano you just mentioned.
So explain it to us simply. What are we actually talking about doing here?
Okay, so the core idea is that we would artificially create a layer of tiny reflective particles really high up in the Earth's sky.
Like a mirror.
Basically, yeah, a very thin, hazy mirror.
Yeah.
And the goal is to bounce a portion of the incoming sunlight right back out into space, before it even has a chance to hit the ground and heat up the surface.
Okay, so for everyone listening, imagine you are walking across this massive black asphalt parking lot.
Oh, the worst feeling.
Right. It's like a glaring, oppressive summer afternoon. The heat is just radiating up right through the soles of your shoes.
You can see the heat waves coming off the pavement.
Exactly. And the sun is just beating down on your shoulders. You're sweating. But then you step under the canopy of this massive old oak tree.
Instant relief.
You instantly feel that wave of relief. The temperature drops, your skin literally stops baking, and the air just feels breathable again.
It's the best feeling on a hot day.
So what we are talking about today is essentially trying to plant a massive invisible shade tree over the entire Earth.
That's exactly it.
We're just turning down the brightness dial on the sun to give the whole globe that feeling of stepping into the shade.
And that physical sensation of relief you get under the tree, that is exactly the mechanism researchers are attempting to scale up to a planetary level.
But doing it for the whole world.
Right. And they know it's theoretically possible because of that volcanic data, that 1991 eruption of Mount Pinatubo. It serves as the ultimate proof of concept in all of these source materials.
Because it actually happened.
Yes. When Pinatubo erupted, it didn't just throw regular ash into the air. It actually injected roughly 20 million tons of sulfur dioxide gas straight up into the sky.
Wait, 20 million tons of gas?
20 million tons!
That is, I can't even picture a number that big, especially for a gas.
It's massive. And once that specific gas, the sulfur dioxide, reached the very upper atmosphere, it chemically reacted with water vapor up there.
Okay.
And it turned into these microscopic droplets of sulfuric acid.
Little acid droplets just floating up there.
Right. They're called aerosols. And over the course of about 3 weeks, those droplets spread out and literally wrapped around the entire globe.
Like a giant blanket.
Exactly. A giant hazy mirror blanket. And they reflected just enough sunlight back into space to drop the average global temperature by a degree Fahrenheit or ½ degree Celsius for nearly 15 months.
So one single mountain blowing its top had enough power to literally change the thermostat of the entire planet for over a year.
It's incredible power, yeah.
But wait, I have to challenge this a little bit. Because it feels like we have pollution in the sky all the time, right?
Oh, lots of it.
Think about the smog over massive industrial cities, or like the smoke from those huge wildfires we keep having. We are pumping stuff into the sky every single day.
Yeah.
Why doesn't our everyday pollution cool the planet the same way a volcano does?
That is a great question, and it gets to the very heart of how our atmosphere is actually structured.
Okay, break it down for us.
Well, the sky isn't just one big, empty room, you know? It's divided into distinct layers, and they have totally different physical rules.
Like a layer cake.
Yeah, exactly. So the layer we live in, where we breathe, where birds fly, and where almost all of our weather happens, that's called the troposphere.
The lower sky.
Right. And you can think of the troposphere like a giant, chaotic washing machine
A washing machine. How so?
because it's full of wind, updrafts, moisture, and most importantly, it's full of rain clouds.
Oh, I see. So when we pump smog or smoke into this lower layer, the washing machine just cleans it out.
Precisely. If pollution gets into the troposphere, it might hang around for a few days, maybe a couple of weeks. But eventually, moisture just gathers around those tiny pollution particles.
They turn into raindrops.
Yeah, they form a raindrop, and the sky washes it right back down to the ground. The troposphere cleans itself constantly.
But Mount Pinatubo was different.
Very different. The explosion was so powerful that it punched right through that lower washing machine layer, and it injected its sulfur into the next layer up.
Which is what?
That's called the stratosphere.
The stratosphere. Okay, so how high up are we talking here? And why is it so different from the lower sky?
So the stratosphere starts about 7 miles above the surface, and it goes up to about 30 miles high.
Okay, that is really high.
And the physical conditions up there are just completely alien compared to the ground. It's incredibly stable, it's very calm, and it is bone dry.
Bone dry, so no moisture at all.
Virtually no water vapor up there. Which means, crucially, there are no rain clouds.
Oh. So because there's no rain, there's literally nothing to wash the particles out.
That is the key right there. Without rain to scrub the air, anything you put into the stratosphere just stays there.
It just sits there.
Yeah, when those volcanic aerosols reach that calm, dry layer, they just floated, suspended, bouncing light away for months on end because nothing was washing them down.
That makes total sense.
And that's the entire premise of solar geoengineering. If humans want to dim the sun, we can't just spray stuff from the ground. It would just rain out.
We have to get it way up high.
Exactly. We have to figure out a way to get millions of tons of reflective material all the way up into the stratosphere where it'll stick around long enough to actually matter.
Okay, I understand the layers now. But I want to go back to the smog thing for a second.
Sure.
Even if the lower sky washes itself out constantly, we are constantly replacing that smog, right? We're burning coal, we're driving cars every single day. So is our everyday pollution doing any bouncing at all?
It absolutely is. And this is a really crucial piece of the climate puzzle that honestly often gets overlooked in the source material.
Really? How so?
Because we are constantly replacing the pollution in that lower layer, there actually is a permanent hazy layer of smog over a lot of the industrialized world.
Just a permanent dirty cloud.
Yeah. And this smog acts as a weak, low-level sunshade. It is actively blocking a significant amount of incoming solar radiation right now.
Wow.
Scientists call it aerosol masking. Our dirty air is literally masking or hiding some of the global warming that our greenhouse gases are causing.
That's wild. So we are already accidentally dimming the sun with our dirty air.
We are.
But wait, that smog is what we are breathing in.
Yeah.
That causes asthma, lung disease, all those public health issues.
Right, which is exactly why we cannot rely on lower level pollution to save us from climate change. It's a deadly trade-off.
We're basically trading our lung health for a little bit of a cooling effect.
Exactly. And the entire goal of stratospheric solar geoengineering is to move that reflective layer far above where any human breathes.
Get out of our lungs and up into space.
Right. If you put the particles in the stratosphere, you get the planetary cooling effect without the direct, immediate respiratory damage to everyone below.
Okay, that makes sense.
And the mathematics of putting it up there, they are absolutely staggering.
Lay the math out for us.
Yeah.
How effective is this stratospheric mirror?
The leverage you get in the stratosphere is just immense. According to the physics outlined in the sources we looked at, 1 single pound of well-placed sulfur in the stratosphere could offset the warming effect of hundreds of thousands of pounds of carbon dioxide in the lower atmosphere.
Wait. 1 pound offsetting hundreds of thousands of pounds.
Yep. The return on investment, purely in terms of temperature reduction, is mathematically astonishing.
That is incredible efficiency. But let's make sure we really picture what this is doing, though.
Let's do it.
So think about a really hot July afternoon, okay?
Okay.
Your car is parked out in a massive parking lot, and all windows are tightly rolled up.
Sounds miserable.
Right. And the direct sunlight passes right through the clear glass. It hits your dark dashboard, and it turns into heat.
Right.
But that heat can't pass back out through the glass easily, so it just gets trapped inside the car.
And it gets so hot.
Exactly. The temperature inside climbs to, like, 140 degrees. That right there is the greenhouse effect. That trapped hot air is our carbon pollution problem.
That's a perfect analogy. The carbon acts just like the rolled-up windows of the car, preventing the heat from venting back out.
Right. Now, dimming the sun is like walking up to that car and putting one of those massive, shiny, reflective cardboard sunshades on the inside of the windshield.
Right, the ones you unfold.
Yeah. Now, putting that sunshade up doesn't roll down the windows, right?
No, the windows are still up.
And it doesn't magically vacuum the hot, trapped air out of the car either.
The air is still trapped.
But it does bounce the incoming sunlight right back out through the glass before it can hit the dashboard.
So it stops the car seats from melting?
Exactly. It cools it down without fixing the air.
That captures the dynamic perfectly. You are treating the immediate symptom, which is the intense, direct solar radiation, without doing anything at all to cure the underlying disease, which is the trapped greenhouse gases.
But this brings up a massive logistical wall, I think. I really have to push back on the sheer physical reality of pulling this off.
Oh, the logistics are a nightmare.
Right, because we don't have a giant volcano on a remote control. We can't just press a big red button and make a mountain explode millions of tons of perfectly mixed sulfur directly into the stratosphere whenever we feel a heat wave coming on.
No, we definitely can't.
And if the stratosphere is 7 to 30 miles straight up, how do humans actually get millions of tons of material up there?
Well, that is the engineering nightmare that basically dominates the technical reports in all the source material.
I can imagine.
Because we can't rely on natural volcanoes, humanity would have to invent, fund, and build a massive continuous delivery service basically to the edge of space.
A delivery service to space.
Yeah, and the proposals for how to actually pull this off, they range from incredibly difficult to bordering on pure science fiction.
I read some of these delivery methods in the reports, and I honestly had to double-check that I wasn't reading a comic book.
They really push the boundaries of modern engineering. So the most analyzed and arguably the most realistic method involves airplanes.
Okay, airplanes. That sounds somewhat normal.
But you can't just rent a fleet of commercial Boeing 747s. Standard passenger jets, even heavy cargo planes, they just do not fly high enough to reach the deep stratosphere where these particles need to go.
Why not? They fly pretty high.
Because the air up there is incredibly thin.
Okay, explain why thin air stops a plane. I mean, an airplane just pushes through the air, right?
An airplane actually relies on the density of the air for two really critical things: lift and combustion.
Okay, lift first.
Right, so first, the wings need thick, dense air to push against in order to keep the massive weight of the plane up in the sky.
Makes sense.
Imagine trying to swim in water, which is dense and supports your weight, right? Yeah.
Now imagine trying to swim in a pool filled with fluffy whipped cream.
Oh, you just sink right to the bottom?
You'd sink. In the stratosphere, the air is so thin that normal wings cannot generate enough lift to hold up a plane carrying thousands of tons of cargo.
Oh, wow. So the wings essentially have nothing to grab onto.
Exactly. And second, jet engines work by sucking in massive amounts of oxygen, mixing it with jet fuel, and igniting it to create thrust.
Right. Fire needs oxygen.
Yep. And in the thin air of the stratosphere, there simply isn't enough oxygen to keep a heavy cargo jet's engines burning. A standard plane would literally suffocate and just lose all power.
That is wild. So how do you fix that? Do you just build a completely different type of airplane?
Yes. Aerospace engineers would have to custom design and manufacture an entirely new class of ultra-high altitude aircraft.
What would they look like?
Well, these planes would need massive, incredibly wide wings to generate lift in that thin air.
Like a glider almost. Yeah, exactly. And highly specialized engines capable of operating in low oxygen environments. And the crazy part is, you wouldn't just need one or two of these.
Oh, right. You need a lot of dust.
You would need a massive global fleet of them, taking off and landing constantly, running a continuous flight schedule every single day of the year.
Just a never-ending conveyor belt of planes flying up to the edge of space.
Round the clock.
That's exhausting just to think about. What are the other ideas if the planes don't work out?
Another heavily debated proposal involves massive weather balloons.
Okay, balloons.
Yeah, the concept is to use giant high-altitude balloons to haul massive tanks of liquid sulfur or other gases all the way up to the stratosphere.
Okay, balloons make sense to me because they naturally float up without needing wide wings or jet engines, right?
Right, they bypass the thin air problem. Once they reach the correct altitude, they would release the gas and then slowly descend.
Okay, but what about the third option I saw in the sources? It mentioned cannons.
Ah, yes. Giant military-grade artillery cannons.
And
The theoretical proposal involves building massive vertical gun barrels and literally shooting specialized artillery shells packed with dust into the upper sky.
they just explode up there.
Yeah, they would detonate and disperse the reflective particles.
Wait, I really have to stop you there. We are talking about using giant guns to shoot at the sky to stop climate change.
I know.
That sounds like something a cartoon villain would invent. Like, it's just so absurd.
It really highlights the extreme desperation in the scientific community right now. When you are tasked with stopping the entire planet from overheating, every physical possibility has to be mathematically modeled, no matter how absurd it sounds.
I guess so.
But look, the delivery vehicle, whether it's custom planes, weather balloons, or giant cannons, that's only half of the engineering equation.
What's the other half?
The other half, which is equally complex, is figuring out what exactly we are delivering.
Right, the payload. We keep talking about sulfur because of the volcano, but is sulfur actually the best material to use?
Well, sulfur is the easiest choice in terms of certainty.
Because we've seen it work.
Exactly. Thanks to Mount Pinatubo and other historical eruptions, scientists know with absolute certainty that sulfur works to cool the planet. There's no guessing involved.
Okay.
However, sulfur comes with devastating, well-documented side effects.
Like what?
If we actively pump millions of tons of sulfur into the stratosphere year after year, eventually gravity pulls it back down to the troposphere.
Right, what goes up must come down.
And when sulfur dioxide mixes with the moisture in the rain clouds down here, it creates acid rain.
Acid rain. I remember learning about this in the 90s. It sounds terrible, but what exactly does acid rain do to the ground?
It alters the entire chemical composition of the soil and the water.
Just poisons it.
Yeah. When sulfuric acid rains down on a forest, it actually leaches essential nutrients out of the dirt, essentially starving the trees.
Wow.
And it's worse for water. It leaches toxic elements like aluminum out of the soil and washes them directly into lakes and rivers.
And aluminum's bad for fish.
It's highly toxic to fish and aquatic life. You could end up destroying freshwater ecosystems entirely.
So we cool the planet down, but we kill the forests and the lakes in the process. I mean, that seems like a totally unacceptable trade-off.
Most scientists agree, and honestly, that isn't even the worst side effect of sulfur.
Wait, it gets worse than acid rain.
It does. In the extreme cold of the stratosphere, sulfur aerosols actively participate in chemical reactions that destroy ozone molecules.
The ozone layer.
Yes, the Earth's natural sunscreen. It blocks the most harmful, cancer-causing ultraviolet radiation from the sun.
So if we use sulfur to build a sunshade to stop global warming, we might accidentally chew a massive hole in the ozone layer.
Exactly. Which would lead to catastrophic spikes in skin cancer and severe crop damage from UV radiation.
Okay, so sulfur is essentially solving a flood by starting a massive fire. We know it works, but it's totally toxic.
Right.
The sources mention looking at alternatives. What else could we possibly spray up there instead?
Because the chemical side effects of sulfur are just so dangerous, atmospheric chemists are aggressively researching inert alternatives.
Inert meaning they don't react chemically.
Right. Materials that will reflect light but won't react with the ozone layer or cause acid rain.
And what are they looking at?
The two most prominent candidates in the research right now are microscopic diamond dust and a very specific type of ground-up chalk called talcite.
Diamond dust. You are telling me scientists want to grind up diamonds and spray them out of custom-built airplanes in the stratosphere?
I am. Scientifically, diamond dust is incredibly appealing.
Because they're shiny.
Exactly. Diamonds are highly refractive, they scatter and bounce light exceptionally well, and they are chemically inert, meaning they wouldn't react with the ozone layer or create acid rain.
What about the chalks?
Calcite, or chalk, is being researched for similar reasons. It has a high albedo, which is just the scientific term for reflectivity.
Okay, I really have to challenge the reality of this. Grinding up diamonds to spray over the entire globe sounds impossibly expensive.
It sounds wild, I know.
But let's set the cost aside for 1 minute and just focus on the physics. If we switch to chalk or diamonds, do we just load it into a plane and dump it out like a bucket of sand?
No, not at all. And this brings us to one of the most complex fluid dynamics hurdles in the entire operation. It's the problem of particle size.
particle size?
Yeah, you cannot just dump material out of an airplane. In the stratosphere, the behavior of microscopic particles is highly volatile.
What happens to them?
If you spray too much material in one specific area, or if the mist isn't perfectly fine, the tiny particles undergo a process called coagulation.
Coagulation, like blood clotting.
Exactly like that. The tiny particles bump into each other in the air, and because of the complex atmospheric forces up there, when they bump, they stick together.
Oh, I see.
Two tiny particles merge into one slightly larger particle, then that one bumps into another, and they merge again.
And they just keep growing.
Right. And as they stick together, they gain mass. They become heavier, and if they get too heavy, the thin air of the stratosphere can no longer hold them up.
So they fall.
They lose their buoyancy and fall rapidly back down to the lower atmosphere before they can do any significant cooling at all.
So if the spray isn't absolutely perfect, the chalk just clumps together like wet flour and falls out of the sky like little rocks.
Precisely. To make this work, the engineering requires an ultra-fine, perfectly even mist.
Okay.
The delivery mechanisms on these hypothetical planes would have to be capable of dispersing microscopic particles so evenly that they never bump into each other. That's the only way to allow them to remain suspended for months or years.
Wow. Okay, so to synthesize this into a mental image for everyone,
Yeah.
we are talking about building a fleet of massive, custom-designed, ultra-high-altitude airplanes.
Right.
And these planes operate like a global fleet of high-flying crop dusters.
Great analogy.
Except, instead of spraying bug spray over a local cornfield, they are flying 20 miles above our heads, spraying an ultra-fine, mathematically perfect mist of microscopic diamond mirrors over the entire globe, nonstop, 24 hours a day.
That is the exact logistical reality of what a full-scale solar geoengineering deployment would look like.
It's just mind-blowing.
It really is an infrastructure project on a scale humanity has never, ever attempted.
Okay, bringing us back to reality for a second. I know I said I would set the cost aside earlier, but I just can't anymore.
Yeah, we have to talk about the money.
A massive global fleet of custom planes, millions of tons of refined materials, nonstop global flight operations. Wait, isn't this going to totally bankrupt the planet?
You would think so.
If it's this complicated, wouldn't it just be cheaper to build massive fields of solar panels, put up millions of wind turbines, and just transition our grid away from dirty fuels in the first place?
You have just touched on what is arguably the single most shocking and frankly terrifying revelation in all of the economic data within these source materials. Yeah. Logic dictates that an artificial planetary sunshade would be astronomically expensive. But the economic models show the exact opposite.
What do they show?
Dimming the sun is terrifyingly cheap.
I need you to define cheap. What are the actual numbers we're talking about?
The current economic estimates for building the specialized planes, sourcing the materials, and running the continuous global flight operations range between $15 billion and $70 billion a year.
Wait, $70 billion is a massive amount of money. That's the gross domestic product of some entire countries?
Right. To a normal citizen or even a small nation, yes, it is a staggering sum. But in the context of global macroeconomics and the fight against climate change,
Yeah?
$70 billion is a rounding error. It is pocket change.
Pocket change.
Think about it. To transition the entire global energy grid, to tear down all the coal plants, replace every gas-powered car with an electric one, and build enough solar and wind power to run the planet that will cost tens of trillions of dollars over decades.
Oh, wow. Yeah, trillions versus billions.
Dimming the sun costs a microscopic fraction of that.
Okay, if it is that cheap, and it cools the planet almost immediately like the volcano did, then what is the problem? That sounds like a miracle solution.
It sounds like a miracle until you look at human psychology and market forces.
Human psychology.
Because it is so cheap and so fast, it creates a massive sociological trap that economists refer to as a moral hazard.
Firewall hazard.
But to understand how dangerous this is, we can just think of it as the painkiller problem.
The painkiller problem. Walk us through that logic.
So imagine you are walking down the stairs, you trip, and you severely break your leg.
Ouch. Okay.
The bone is fractured, the muscle is torn, your leg is swelling up, and the pain is absolutely agonizing.
Right.
You go to the emergency room, and instead of taking an x-ray, setting the bone, and putting on a cast to heal the injury, the doctor just hands you a massive dose of highly addictive opioid painkillers.
Okay, so the opioids kick in, the pain goes away instantly, I feel totally fine.
You feel fantastic. The pain is completely gone, but the bone is still broken. Right.
And because you don't feel the pain, you stand up and start walking around on that broken leg. You go for a jog.
Oh, no.
And by doing that, you grind the fractured bone into dust, completely destroying your leg forever.
Wow.
Dimming the sun is the opioid painkiller for the planet.
Because it only treats the symptom of heat.
Exactly. If we deploy the global sunshade, the Earth's average temperature will go down, the brutal summer heat waves will stop, the immediate agonizing pain of global warming will vanish.
Which sounds great.
It sounds great. But the underlying disease, which is the billions of tons of carbon pollution being pumped into the air by fossil fuel companies, that hasn't been cured at all.
The bone is still broken.
Right. And because society feels comfortable under the sunshade, governments and corporations will lose the political will to spend trillions of dollars transitioning to clean energy.
Oh, I see. They'll just say, why bother? We fixed it.
Exactly. They will just keep burning oil and coal, and the carbon will keep piling up in the background. Wait, I have to challenge this logic a little. If the planet is cool, why do we actually care if the carbon is still piling up? If the sunshade stops the heat, doesn't that solve the problem for us?
That is the fatal flaw in the painkiller strategy. Carbon dioxide does a lot more than just trap heat in the air.
What else does it do?
A massive percentage of the carbon dioxide we pump into the atmosphere gets absorbed directly into the world's oceans.
Okay.
And when carbon dioxide mixes with seawater, it triggers a chemical reaction that creates carbonic acid.
Carbonic acid.
This process is called ocean acidification, and the sunshade does absolutely nothing to stop it.
So the oceans are literally turning into acid while we sit comfortably in the shade on land. What does carbonic acid actually do to the water?
It destroys the fundamental building blocks of marine life. Animals like coral reefs, oysters, and certain types of plankton rely on free carbonate ions in the water to build their hard shells and skeletons.
Okay, so they need the carbonate.
But the carbonic acid chemically binds to those carbonate ions, basically stealing them away. The marine life literally cannot build their skeletons. In highly acidic water, existing coral skeletons can actually begin to dissolve.
Just melt away.
Yeah. So even if the air feels perfectly cool because of our sunshade, our oceans will turn into a lifeless acidic soup. The entire marine food web could collapse.
That is a terrifying reality check. Let me try an analogy here that might hit closer to home for anyone listening who has ever procrastinated on doing their chores.
Oh, I know that feeling.
Relying on this sunshade is like sweeping all of your house's dirt under a giant rug because you have important guests coming over.
Just hide it all.
You just frantically sweep it all under there. When the guests arrive, the living room looks perfectly clean. Everyone is impressed.
But the dirt is still there.
Right. But imagine that dirt is highly corrosive. It isn't just sitting there out of sight. It is actively eating away at the floorboards right under your feet where you're standing on the rug.
Wow.
Eventually, the floor is just going to cave in entirely.
The corrosive dirt is the perfect addition to that analogy. That is exactly what carbon pollution does to the oceans.
It eats the floorboards.
By giving the world a cheap, incredibly fast way to hide the heat, we remove the motivation to actually clean up the corrosive mess. We hand the fossil fuel industry a get-out-of-jail-free card to just keep polluting indefinitely.
Okay, this leads to a massive, glaring security question for me. If this technology is essentially just a planetary painkiller, and we just established it only costs a few $billions a year.
Which is nothing globally.
Right. What stops one single grumpy billionaire, or even one rogue country that is tired of suffering from heat waves, from just buying a fleet of planes and doing this themselves? Do they have to get permission from the rest of the world?
You have just articulated the exact nightmare scenario that keeps global security and military experts awake at night.
Really?
Yes. The concept you were describing is called unilateral deployment.
Unilateral, meaning one side does it.
Exactly. That means one single actor, whether it's a wealthy nation, a coalition of small island states facing rising sea levels, or even an ultra-wealthy private citizen, decides to pull the trigger and dim the sun entirely on their own.
And to answer my question about permission.
Right now, very little stops them.
Wait, hold on. We're talking about altering the atmosphere of the entire Earth. There is no international law against this. There is no global sky police.
Surprisingly, no. There is no comprehensive, legally binding international treaty that explicitly bans a nation from launching a fleet of airplanes from their own sovereign soil and releasing inert dust into the stratosphere above their own country.
But they're above their own country. How does that affect everyone else?
Because the stratosphere doesn't have borders the way land does, once the particles are up there, the high-altitude winds will grab them and distribute them globally.
Oh, of course. The wind just blows it everywhere.
If a country is suffering from devastating, deadly heat waves that are killing their citizens and destroying their crops, and their leaders realize they can stop the heat in a matter of weeks for a few $billions,
The temptation would be huge.
the geopolitical temptation to just launch the planes will be overwhelming.
But if they launch the planes from their country, and the winds carry the dust everywhere, the sky is connected. They're basically making a decision for the entire planet.
Exactly. And that interconnectedness leads to the geopolitical crisis known as the global thermostat problem.
The global thermostat.
Yeah, if you deploy a sunshade, the cooling effect is not perfectly smooth or even across the globe. You cannot just set the Earth to a comfortable 72 degrees in every single country.
Right, because the planet is a complex system of oceans, mountains, and deserts.
Exactly.
So who gets to hold the remote control? Who decides what temperature the Earth should actually be?
That is where the potential for global conflict just explodes.
Give us a scenario.
Let's imagine one. Say a nation near the equator is facing unlivable, lethal heat waves, so they unilaterally deploy the sunshade to cool things down and save their people.
Totally understandable from their perspective.
But much further north, a country like Russia might actually be relying on global warming.
Relying on it.
A warmer planet thaws out their frozen Siberian tundra, giving them massive new tracts of usable farmland and opening up the Arctic Ocean for lucrative shipping routes.
So Russia wants the heat, and the equatorial country wants the cold.
Yes. Or consider a situation where India wants a cooler planet to protect their population from heat stroke, but a neighboring nation relies on those warmer seasonal temperatures to drive a specific agricultural economy.
It's a zero-sum game.
Exactly. If one nation alters the sky to benefit themselves, they are almost certainly going to damage the economy or the climate of another nation.
You know, for you listening, it's like living in a massive, sprawling apartment building where only one tenant has the universal remote control for the central air conditioning.
Oh.
No matter what temperature they punch into the thermostat, half the building is going to be shivering in sweaters, the other half's going to be sweating, and every single person is going to be furious at the guy holding the remote.
The apartment building analogy is spot on, but the anger wouldn't just be over the temperature on the thermometer.
What else would they be angry about?
Dimming the sun comes with major, highly visible, and very physical side effects that every single person on Earth will experience. For one, if we pump enough particles into the stratosphere to meaningfully cool the Earth, the physical color of the sky will actually change.
The color of the sky. What do you mean by that?
The blue sky we see today is the result of sunlight passing through a clean atmosphere.
Right, scattering the blue light.
But if we fill the stratosphere with billions of tiny reflective particles, those particles will scatter the light in a completely different way.
So it won't be blue.
The sky won't be that deep, crisp, endless blue anymore. It will permanently turn a hazy, milky white.
Wait, are you saying we would never see a clear blue sky again?
Depending on how thick the sunshade is, the sky would be permanently hazy. Sunsets might become violently colorful due to all the extra light scattering, but the crisp blue day, that would be gone.
That is incredibly sad to think about.
And this light scattering has a direct economic impact, too. Because the direct sunlight is being scattered and diffused by the particles, it actually severely reduces the efficiency of solar panels down on the ground.
Wait, so by dimming the sun to fight climate change, we accidentally cripple our ability to generate clean solar energy.
That's what the models show, yeah.
That is a brutal irony. But surely a milky sky and less solar power aren't the worst things that could happen. What about the weather itself?
The weather is where the true danger lies. Changing how much direct sunlight hits the Earth's surface fundamentally shifts global precipitation and rain patterns.
It messes with the rain.
We know this for a fact because historical data from large volcanic eruptions shows massive shifts in rainfall. The most terrifying risk of a global sunshade is that it could accidentally shift, weaken, or entirely dry up the seasonal monsoons in Asia and Africa.
The monsoons.
Ah.
Explain how a sunshade thousands of miles away up in the stratosphere can stop it from raining in Asia.
Okay, so the monsoon is essentially a giant thermal engine. In the summer, the massive landmass of the Asian continent heats up intensely.
Hot air rises.
Exactly. As that hot air rises, it creates a massive, low-pressure vacuum over the land. This vacuum basically sucks in cooler, incredibly moist air from the Indian Ocean.
Like a giant vacuum cleaner.
Right. And when that wet ocean air hits the land, it dumps massive amounts of rain.
And that's the monsoon.
Now, if you put a sunshade over the Earth, the Asian landmass doesn't heat up as much. The hot air doesn't rise as forcefully. The vacuum is much weaker.
Oh, I see.
Therefore, the moist ocean air never gets pulled inland. The engine essentially stalls out.
And if the wet air doesn't come inland, the rains fail. And billions of people rely on those specific monsoons to water their crops.
Exactly. If the monsoon fails, you aren't just looking at a bad harvest. You are looking at unprecedented, multi-continental mass starvation.
Okay, let's play this out realistically. If country A launches the planes because they are too hot, and the following year the monsoon fails, and country B suddenly has no rain and all their crops die, doesn't country B declare war?
They very well might.
And legally, how do you even prove it? How does country B prove to the United Nations that the airplanes caused their specific drought?
You have identified the core legal nightmare that makes this whole thing so volatile. In the real world, the climate is chaotic. Droughts happen naturally all the time.
Right.
If country B suffers a catastrophic drought and blames the sunshade, country A will simply look at them and say, droughts have happened for millions of years. You cannot definitively prove that our airplanes caused your specific lack of rain.
Because weather is too complicated to trace back to a single fleet of planes.
Exactly. Scientifically, it is incredibly difficult to prove a direct one-to-one cause and effect relationship between a global aerosol layer and a localized weather event.
So you can't prove it in court.
Traditional international liability laws completely break down here. You can't just sue a neighboring country for a drought when the atmosphere is a shared chaotic system.
But the people aren't going to care about the legal nuances.
No. When billions of people are starving and their leaders need someone to blame, they aren't going to care about the nuances of atmospheric modeling. They're going to blame the planes they can physically see in the hazy sky.
So they go to war.
The risk of geopolitical collapse, border conflicts, or even a world war skyrocketing over this is immense.
Okay, my anxiety is totally through the roof right now.
It's a lot, I know.
Spraying the entire stratosphere with particles, turning the sky milky white, shitching the monsoons, and risking a world war seems like a recipe for absolute disaster. The whole global thermostat thing seems way too big to manage.
It's massively risky.
So are there any alternative ideas in the sources? Are scientists looking at localized, smaller-scale ways to bounce light that don't involve wrapping the entire Earth in a volatile chemical blanket?
Yes, thankfully. Because the risks of stratospheric spraying are so heavily criticized, researchers have developed proposals for localized, lower-altitude interventions.
Lower altitude meaning the troposphere.
Right, the washing machine layer. The sources outline two main alternative methods that focus on the lower sky rather than the stratosphere. The first method is called marine cloud brightening.
Brightening clouds.
Yeah.
How do you make a cloud brighter? Do you just shine a giant light on it?
No. It relies on altering the actual physical composition of the cloud itself.
Okay.
This method focuses specifically on the low-hanging gray marine clouds that blanket large portions of the world's oceans.
The thick ones over the water.
Right. The concept is to deploy fleets of autonomous ships out into the sea. These ships would pump ocean water through highly specialized nozzles, spraying an ultrafine mist of plain sea salt high into the air, right up into those low clouds.
Okay, so we are spraying salt instead of sulfur. How does salt make the cloud brighter?
It comes down to basic cloud physics. For a cloud to form, water vapor needs something physical to grab onto, like a microscopic speck of dust, or in this case, a salt crystal.
Like a seed.
Exactly, they're called condensation nuclei. If you introduce billions of tiny new salt crystals into an existing cloud, the water vapor spreads out and gathers around these new seeds.
Okay, so what happens?
This forces the cloud to create millions of newly formed, much smaller water droplets rather than fewer, larger droplets.
And smaller droplets make a difference.
A massive difference. A cloud made of millions of tiny droplets has a much higher surface area than a cloud made of large, heavy droplets.
More surface area to bounce light.
Exactly. And more surface area means a higher reflectivity. the cloud becomes noticeably whiter and denser.
So a whiter cloud bounces more sunlight back into space before it can hit the dark ocean below.
Exactly. And the most compelling part of marine cloud brightening is that we already know it works because humans are currently doing it by accident.
Wait, we are? How?
Satellites orbiting the Earth can easily see what atmospheric scientists call ship tracks.
Ship tracks, like tire tracks on a dirt road.
Visually, it's very similar, yes.
Right.
When massive cargo ships traverse the oceans burning heavy, dirty fuel, the exhaust from their smokestacks is full of microscopic pollution particles.
Which act like the seeds.
Right, they act as condensation nuclei, just like the salt would. As the ship moves, a bright, highly reflective, distinct line of white clouds forms directly behind it, following its path across the ocean.
Oh, wow.
The proposal for marine cloud brightening is simply to replicate those accidental ship tracks on purpose, but using pristine, clean sea salt instead of dirty, toxic engine exhaust.
I really, really like the sound of that. Using plain sea salt in ocean water feels infinitely safer than spraying sulfur or grinding up diamonds.
It's definitely a more natural approach.
So what is the second localized method mentioned in the sources?
The second method focuses on a completely different type of cloud and works in the exact opposite way. It is called cirrus cloud thinning.
Cirrus clouds. Which ones are those?
Cirrus clouds are those very high, wispy, thin clouds made of ice crystals that you often see on a clear day.
Right, they look like little feathers high up in the sky.
Exactly. Now, unlike the low, thick, gray marine clouds that act like shields blocking incoming sunlight, cirrus clouds actually let most incoming sunlight pass right through them.
Okay.
But they have a dangerous secondary effect. When the Earth absorbs that sunlight and tries to radiate the heat back out into space as infrared energy, these high, icy cirrus clouds trap that outgoing heat.
Oh, I see.
They act exactly like a thermal blanket wrapped tightly around the Earth.
So they're trapping the exact heat that we are desperately trying to get rid of.
Right. They're actively contributing to the greenhouse effect. So the intervention proposed in cirrus cloud thinning isn't to make them brighter. It is to thin them out or break them up entirely.
Break the blanket.
The idea is to fly planes through these clouds and inject specific aerosols that force the ice crystals to grow too large, causing them to fall out of the sky as precipitation.
Just make them rain or snow out.
Exactly. By destroying the cirrus clouds, we essentially punch massive holes in the atmospheric blanket, allowing the Earth's trapped heat to rapidly vent out into the deep freeze of space.
Okay, let's make sure these two cloud methods are totally clear for everyone listening.
Do it.
Marine cloud brightening. The first method is like choosing to wear a crisp white t-shirt on a hot summer afternoon instead of a black one.
Perfect.
The white fabric acts as a shield, bouncing the incoming solar radiation away before it can heat up your skin.
Yes.
Now, cirrus cloud thinning, the second method, is like waking up in the middle of the night sweating because you are way too hot in bed.
We've all been there.
You kick your heavy down quilt off your legs to let your trapped body heat rapidly escape into the cool air of the bedroom.
Both analogies perfectly capture the thermal physics of what is happening there. One method builds a shield to bounce heat away before it arrives. The other method removes a blanket to let trapped heat escape.
These cloud methods sound so much more reasonable than building a global stratospheric sunshade. We are just using natural salt water or breaking up ice clouds.
They are definitely less aggressive.
But I see a massive structural flaw here.
What's that?
Earlier, we established that the troposphere is like a washing machine. Clouds blow away, they rain out, the weather is constantly churning.
Right.
So if we rely on ships spraying salt to keep the oceans cool, what happens if the ships break down? Or what if a country goes bankrupt and they just have to stop spraying?
You have just zeroed in on the absolute biggest, most catastrophic risk discussed in all of the source material.
Really? The biggest?
Yes. It is the dark shadow hanging over every single one of these geoengineering proposals. It is a concept called termination shock.
Termination shock. It sounds like the title of a 1990s action movie. What exactly is it?
It is the terrifying reality of relying on a temporary artificial shield to hold back a permanent physical force. Whether you are using ships to spray salt into marine clouds or custom planes to spray sulfur into the stratosphere, the reflective particles do not stay in the sky forever.
Because gravity and rain.
Right. In the clouds, they rain out in days. Even in the calm stratosphere, gravity eventually pulls the sulfur down over the course of 6 to 12 months.
So they always fall.
Always. To maintain the cooling effect, you have to keep spraying, nonstop, day after day, year after year, decade after decade.
It requires a permanent, unbreakable commitment to continuous delivery.
Exactly. Now, imagine a scenario where humanity successfully deploys a stratospheric sunshade and we maintain it perfectly for 50 years.
Okay, 50 years of success.
During those 50 years, the global temperature feels totally normal. Society is comfortable.
The painkiller's working.
Right. And because everyone is comfortable, governments abandon clean energy projects. We just keep burning coal, oil, and gas. The carbon pollution continues to build up massively in the atmosphere, thickening the greenhouse gas layer.
But we don't feel the heat because the sunshade is blocking the sun.
We don't feel it, but the physical reality of that trapped energy doesn't just go away. A colossal, unimaginable amount of thermal energy builds up behind the artificial shield.
Like a dam holding back water.
Or exactly like building pressure inside a sealed pressure cooker with the heat turned all the way up.
The pressure just keeps mounting in the background.
Exactly.
Yeah.
Now, what happens if the planes suddenly stop flying?
Why would a vital planetary system like that ever stop, though, if we know we need it?
The sources outline numerous highly plausible scenarios. A massive global war breaks out, and the custom planes are targeted and destroyed by an enemy.
Oh, that makes sense.
Or catastrophic global economic collapse occurs, and governments literally cannot afford to buy the jet fuel. Or even a severe space weather event, like a massive solar flare, knocks out all global navigation satellites, grounding the entire fleet.
So there are plenty of ways it could fail.
If the spraying stops for any reason, all of those reflective particles will fall out of the stratosphere within a matter of months.
And the sunshade just vanishes.
The sunshade disappears entirely. But all of that accumulated carbon pollution, 50 years worth of thick greenhouse gases, is still sitting there.
Waiting.
If the sun hits that unmasked carbon, the Earth would experience 50 years worth of global warming compressed into a time frame of just a few months.
Wait, 50 years of gradual climate change hitting us in one single summer.
Yes. And it is the velocity of that change that is so deadly. The temperature wouldn't just slowly creep up, it would violently vertically spike.
Why is the speed so important?
Because if the Earth warms slowly over a century, biology has a chance. Plant species can slowly migrate away from the equator. Animals can adapt their habitats. Human farmers can slowly transition to different heat-resistant crops.
We can adapt.
But if the temperature spikes by 2 or 3 degrees Celsius in a single year, the biological shock to the system is absolute.
So ecosystems just shatter.
They evaporate. Forests would spontaneously combust into continent-wide wildfires because the trees couldn't adapt to the sudden heat. Entire marine ecosystems would boil. Human societies would face simultaneous, devastating crop failures across the entire globe.
Oh my
There would
God.
be absolutely no time to adapt. It would be an extinction-level event for countless species.
Okay, that paints a vivid, paralyzing picture. Imagine you take a thick rubber band and you slowly stretch it back as far as it can possibly go.
Okay.
The sunshade is your hand holding that rubber band back. As long as your hand is strong, it feels stable. But the tension built up in that rubber band is immense.
Lots of potential energy.
If your hand slips or if your arm gets tired and you just let go, that is termination shock. The rubber band doesn't slowly, gently return to its normal shape.
No, it snaps.
It violently snaps back all at once with devastating force, breaking whatever happens to be in its path.
The rubber band analogy is completely accurate. The tension is the accumulated carbon. The sources actually use a classical metaphor for this scenario. They call it a planetary sword of Damocles.
A sword hanging by a thread.
By deploying solar geoengineering without cutting carbon, we would be willingly hanging a deadly sword over the neck of humanity, suspended by a single, fragile thread, just praying that the thread never, ever breaks.
So I really have to ask, and I am asking this with genuine structural pushback on this whole concept we've been talking about, are we accidentally designing a doomsday machine here?
It's a valid question.
If the failure of this system results in a global biological collapse that is infinitely faster and more violent than regular climate change, why would we ever consider turning it on? Is this cure actually a fate much worse than the original disease?
To answer that, we really must zoom out and look at the agonizing ethical mathematics the scientific community is struggling with.
What are they weighing against each other?
It forces us to weigh two nightmarish scenarios against each other. We have to weigh the terrifying, catastrophic risk of the rubber band snapping against the very real, very present-day disaster of actual ongoing global warming, which is currently destroying lives and habitats today.
Right now.
And I will tell you, the scientific community is heavily, bitterly divided on how to navigate this.
Break down the factions for us. What do the different experts say in the reports?
On one side, you have major, highly respected scientific coalitions like Project Drawdown. They have looked at all the aerosol physics, the weather modeling, and the geopolitical risks, and they have concluded that solar geoengineering is strictly, unequivocally not recommended.
They just flat out draw a line in the sand and say, do not touch this.
Yes. Their core argument is based heavily on the moral hazard problem we discussed earlier.
The painkiller problem.
They argue that it is far too risky, the side effects on the monsoons are too dangerous, and most importantly, it acts as a massive distraction.
A distraction from fixing the real problem.
They believe that even funding research into sun dimming gives politicians and fossil fuel executives an excuse to delay doing the hard, expensive work of transitioning to clean energy. They believe the only true path forward is cutting emissions, no matter how hard it is.
Okay, that makes total logical sense.
Yeah.
But there must be scientists who think it's worth the risk. Otherwise, we wouldn't have entire research papers outlining how to build the airplanes.
There are. Other climate models and atmospheric experts present a very different, highly pragmatic perspective.
What's their take?
They argue that we do not have to use a massive, thick sunshade to completely stop global warming in its tracks.
What do they want to do instead?
What if, instead of a thick shield, we just use a very thin, carefully controlled sunshade? What if we deploy just enough particles to shave off the most extreme, lethal peaks of the heat waves while we spend the next 50 years transitioning to clean energy?
Oh, I see. So not a cure, just taking the edge off the heat.
Exactly. The strategy is called peak shaving. If we just shave off the peak temperatures for the next few decades, the models suggest it could prevent unimaginable suffering in developing nations that are currently baking.
Saving lives today.
Right. It could be the only physical mechanism capable of saving the world's remaining coral reefs from completely boiling in the next 20 years. It could reduce the thermal energy in the oceans just enough to weaken the intensity of catastrophic tropical hurricanes that tear apart coastal cities.
So they're arguing that it is a temporary bridge, not a permanent solution.
Yes, and their ethical argument is incredibly powerful. They argue that refusing to use this tool, knowing that millions of people are suffering and dying from extreme heat today, is its own kind of moral failure.
It's a brutal, impossible calculation.
Mm.
Let's imagine you are driving a car that has lost its brakes, and you are speeding down a mountain road heading straight for a cliff.
Terrifying.
Dimming the sun is like choosing to deliberately steer that runaway car off the pavement and into a deep, rocky mud pit to force it to slow down. It is going to completely ruin the car. It is incredibly violent. You might flip over. The passengers are going to get hurt, and nobody in their right mind wants to do it. But it might be the only physical option you have left that is better than flying off the fatal cliff that is dead ahead.
That is a phenomenal synthesis of the peak shaving argument. You are actively choosing a parable damaging option solely to avoid the completely fatal option.
But how do we even know if it'll work?
Well, that brings us to the current gridlock in the scientific community. How do we even know if steering the car into the mud pit will actually slow us down if we have never tested it?
Wait, we haven't tested any of this. I know we can't test a global sunshade, but surely we are testing the delivery mechanisms, right? Like the balloons.
We aren't, and that is the problem. To know if the nozzles work, to know how the particles coagulate in the real atmosphere, scientists desperately need to run small, highly controlled outdoor experiments.
But why don't they?
Because the public fear surrounding geoengineering is so intense that almost every time a university research team tries to launch a tiny weather balloon just to test a spray nozzle, massive public protests erupt and force the university or the government to cancel the experiment.
So we are just arguing over theoretical computer models.
Entirely. We are flying completely blind. And the researchers argue that without small-scale outdoor testing today, if a desperate country decides to unilaterally launch a real sunshade 10 years from now, we won't have any real-world data to guide them.
We won't know what's going to happen.
We won't know the actual side effects until they are already happening on a planetary scale.
This is incredibly heavy. We are trapped between a boiling planet and a potentially world-ending technological gamble. But before we wrap up this deep dive, is there anything else from the historical data or the sources that totally surprised you?
Actually, yes. There is one final, truly mind-bending paradox that the sources leave us with, and it completely reframes this entire conversation.
Oh, really?
We talked earlier about aerosol masking, right? how human smog and air pollution from coal plants and factories currently block some sunlight.
Right. We are accidentally cooling the Earth a little bit
Mm.
because our lower sky is full of dirty, reflective smog.
Well, let's look at what is happening globally right now. Across the world, governments are finally aggressively cracking down on air pollution.
Which is great.
We are shutting down the dirtiest coal plants. We are installing high-tech chemical scrubbers on factory smokestacks. In 2020, the global shipping industry implemented strict mandates requiring massive cargo ships to use low-sulfur fuels.
Okay, good.
We are doing all of this to save millions of people from dying of asthma, lung cancer, and respiratory diseases.
Which is undeniably a good thing. We want clean air to breathe. Public health absolutely demands it.
It is essential for human health. But as we clean up the air, that accidental massive smog sunshade is rapidly disappearing.
Oh, no.
The skies over industrial centers and shipping lanes are getting clearer and cleaner every single day. And because the skies are clearing, the aerosol masking effect is vanishing.
The shield is going away.
Significantly more direct, harsh sunlight is suddenly hitting the Earth's surface and the oceans.
Wait. If the sunshade vanishes...
Yes. In a strange, terrifying way, humanity is already doing solar geoengineering, and we have been doing it by accident since the Industrial Revolution.
Wow.
And now, by cleaning up our air for the sake of our lungs, we are actively removing that historical sunshade. Because the air is suddenly cleaner, the Earth is going to absorb more heat, and it is going to heat up significantly faster in the coming years than the models previously predicted.
Are you saying that cleaning up our air pollution is actively causing a mini termination shock right now?
Precisely. We are currently experiencing a localized termination shock. We are already trapped inside the very experiment that we are too terrified to run on purpose. The warming we are seeing accelerate right now is partly because we're finally breathing clean air.
That is an absolutely profound paradox. The idea that doing the morally right, medically necessary thing for human health might actually accelerate the climate tipping points. It just exposes how incredibly delicate and terrifyingly interconnected the physical balance of this planet really is. Thanks for coming along on this deep dive with us. Remember, follow us on your favorite podcast platform, and see you on the next dive.